Hello everyone, my name is Natanael, and I'm honored to present our research at the 15th IEEE Symposium on Computer Applications and Industrial Electronics. This research was conducted together with Richard Vincentius and Professor Dr. Dyah Erny Herwindiati from Tarumanagara University, Indonesia. Today, I'll be sharing our study about the comparison of linear and radial basis function kernels in supervector machine for race variety classification. First, let's begin by understanding why race variety classification is important. So, rice is one of the most consumed staple food worldwide, feeding billions of people every day. However, not all rice varieties are the same. Different types of rice have unique characteristics that affect quality control and market segmentation. Traditionally, rice variety classification relies on manual inspection, which is often time-consuming, labor-intensive, and prone to human error. With the advancement of machine learning, we can now automate the classification process using supervector machine, or SVM, make it faster, more reliable, and scalable. Now, let's move on to the objective of our study. In this research, we aim to achieve three main objectives. The first objective is to compare the performance of two SVM kernels, namely the linear kernel and the radial basis function, or RBF kernel, in rice variety classification. The second objective is to utilize principal component analysis, or PCA, to reduce the dimensionality of our dataset while retaining essential information. Lastly, the third objective is to analyze the trade-offs between classification accuracy and computational efficiency in both kernels. To achieve these goals, we worked with a large dataset of rice grain images. For this study, we used a dataset containing 75,000 rice grain images representing 5 different rice varieties. These 5 varieties are Arborio, Basmati, Ipsala, Jasmine, and Karasadak. To extract meaningful features from these images, we used RGB histograms and then applied PCA to retain 90% of the dataset's variance while reducing dimensionality. Next, let's take a look at the methodology used in our research. Our research follows a step-by-step process consisting of 5 key stages. First, we have image acquisition. Here, we capture high-quality images using a high-resolution CCD camera, ensuring that lighting conditions were controlled to maintain image consistency. The second step, we conducted image processing. The step includes noise reduction and feature extraction using RGB histograms, capture the color distribution of the rice grains. Third, we perform feature extraction. We apply principal component analysis, or PCA, to transform the structured histogram data into a lower dimensional feature space while preserving the most important information. The first step, we implement classification. We train an SVM model using 2 different kernels, the linear kernel and the RBF kernel. And the final step is evaluation. To measure the effectiveness of our model, we use key performance metrics such as accuracy, precision, recall, and F1 score. Now, let's explore how we collected and processed the images in more detail. To ensure high-quality data collection, we designed a custom-built imaging box equipped with controlled lighting and a fixed camera height. After capturing the images, we converted them into a digital format and extracted the RGB histogram features, which provide a numerical representation of color distribution in each grain. Once the images were pre-processed, we applied the PCA to optimize feature representation. Principal component analysis, or PCA, helps us reduce high-dimensional data while retaining key information. PCA works by transforming RGB histograms into a new set of orthogonal components, ranking them based on the amount of variance they capture. By keeping only the top components that account for 90% of variance, we successfully reduce computational complexity while maintaining classification accuracy. Now, let's move on to the classification process using support vector machine. Support vector machines, or SVM, are powerful supervised learning models that find the optimal hyperplane to separate different classes. In our study, we trained and tested two different kernels. That is the linear kernel, which is computationally efficient and performs well when the data is linear separable, and the radial basis function, or RBF kernel, which transforms the data into a higher dimensional space, making it better suited for complex and nonlinear classification problems. To measure the model performance, we evaluate four key metrics. The first one is accuracy, which tells us the overall correctness of the predictions. Next, precision, which measures the proportion of correctly classified positive samples out of all predicted positive samples. Next, there's a recall, which indicates how well the model identifies all actual positive cases. And lastly, there's F1 score, which is balance, precision, and recall, providing a single performance metric. Now that we understand the evaluation criteria, let's move on to the model training and testing. So basically, here we split the dataset into two parts. 70% for training, consisting of 52,500 images, and 30% for testing, which includes 22,500 images. By using Bayesian hyperparameter tuning, we optimized the model, and the best parameters were for linear kernel, the C, or the regularization parameter, equals to 1.1234. For the RBF kernel, the regularization parameter equals to 115.3399, with the gamma, or the kernel coefficient, equals to 0.0003. Now, let's see how its model performed. The linear kernel achieved an accuracy of 83.28%, performing well for Uppsala and Kersedak, but struggling with Basmati and Jasmine. Meanwhile, the RBF kernel performed slightly better, reaching 84.80%, handling nonlinear patterns more effectively. So we have seen the individual performance of both kernels. Now, let's directly compare them. When we're looking at the efficiency, the linear kernel is faster and computationally lightweight, making it a great choice for real-time applications or when we're working with limited hardware resources. However, when it comes into accuracy, the RBF kernel consistently performs better, especially for nonlinear separable data like race varieties in our dataset. So, if speed and efficiency are your main concerns, go with the linear kernel. If accuracy and flexibility are your priority, the RBF kernel is better choice, though it comes at the cost of higher computational demand. With this comparison in mind, let's wrap up with the final conclusion and future recommendations. So to summarize it all, our study found that the RBF kernel outperforms the linear kernel in classification accuracy, making it ideal for applications where precision is critical. The linear kernel remains a strong choice for situations requiring a fast processing and lower computational power. And also, there are several directions for future research. First, we can explore more advanced feature extraction techniques to enhance the classification accuracy even further. By incorporating additional image processing methods or leveraging deep learning-based feature extraction, we could improve the model's ability to distinguish the similar race variety. Second one, while the RBF kernel performed well, its computational cost remains a challenge. Future work could focus on optimizing the RBF kernel, either by fine-tuning its parameters or exploring approximation methods to make it more efficient without sacrificing the accuracy. And with that, this concludes my presentation. So thank you for your attention. I appreciate your time and interest in our research.